Hey everybody, let's look at lesson 6. We're going to be graphing rational functions today, also analyzing them and having some rational function fun. So exactly what is a rational function? Well, when we have a polynomial that's in the numerator and a polynomial in the denominator, then a rational function is the quotient between the numerator and the denominator. And when we're finding domain, the domain of x includes all the real numbers except for values that cause division by 0. Domain restrictions come from the values that make the denominator 0. Here we are in example 1. We're going to use those properties to find the domain. So if you notice in the denominator, you have x squared minus 3x plus 2, and we have x plus 7 in the top. So we want to see if there are factors for the denominator that would multiply to give 2 and add up to be negative 3. So I think we would have to have a positive number and a negative number. And if it was 2 times 1, I take that back. We need 2 negative numbers, 2 negative factors, since our 2 is positive here. So 2 times 1 would give us positive 2, and negative 2 plus negative 1 would add up to be negative 3. And we had just said that any values in the denominator that cause the denominator to be 0, those would be not in the domain. So we would not have 1 in the domain, and we would not be allowed to have 2 in the domain. These would be vertical asymptotes in our graph. They would be infinite discontinuities, we call those. So vertical asymptotes cause division by 0, or division by 0 causes a vertical asymptote. And in that case, the domain would be all real numbers except for the 2 breaks in the graph. So the first break would happen at 1, and then we would go from 1 to 2, and then we would go from 2 to infinity. So the domain is all reals except 1 and 2. Horizontal asymptotes, we can have vertical asymptotes and horizontal asymptotes. In this example, the graph behavior is going to approach the vertical line, and it appears like that vertical line is at negative 3. Is that right? Does it look like that to you? So we got an infinite discontinuity at x equals negative 3. So the definition of a vertical asymptote is when the limit as you approach your asymptote from the left, or the limit as you approach the asymptote from the right, are heading to an infinite value. And here you can see that happening if you look. As we approach negative 3 from the left, so this is as x approaches negative 3 from the left, you see what our y values are doing? The y values are tending to go upward. And then on the other side, as we approach negative 3 from the right, so approaching negative 3 from the right, the y values are heading downward. So as x approaches negative 3 from the right, the y's are going down. And these two infinite behaviors, in this case they're in opposite directions. So on one side it's bounded downward, and on the other side bounded upward. We say that's the definition for a vertical asymptote. So we could take this pre-calculus way of writing things and turn that into a more formal limit approach, and we could say the limit as x approaches negative 3 from the left, and our function is called, well, we're going to call it f of x. The graph is going up on the left. And then on the right, it would look the same, just backwards. Limit as x approaches -3 from the right. Limit as x approaches -3 from the right. The y values are going down. Okay, so we can use limit notation. And this is our vertical asymptote. Our a value is -3. And horizontal asymptotes, same thing, only different. A horizontal asymptote is going to be y equals equation, where a vertical asymptote is an x equals type of equation. So x equals -3, or what's this one look like? Y equals 2. And this one is related to the end behavior. So when a graph tends toward positive or negative infinity along a line, then we're going to say that y equals 2 is our horizontal asymptote. So the limit as we approach negative infinity on the graph of f is heading to +2 in either direction. So y equals 2 is the horizontal asymptote. Now, here's one thing you might have a misconception about from Algebra 2. It is definitely possible to cross a horizontal asymptote. Remember, horizontal asymptotes are behavior at the extremes. When I'm looking around a neighborhood here at the origin, I could cross an asymptote and still be asymptotic at the end behavior or at the extremes. So just be aware of that. So we know that both holes and vertical asymptotes are found when we set the denominator equal to 0. And one of the things we want to learn in this lesson is kind of like a procedure for what to do first, second, third when you're trying to solve or simplify or graph. So you want to simplify a rational function by factoring the numerator and the denominator. So we want to try that first always. And then you want to find the zeros. What makes the numerator 0? What makes the denominator 0? If a 0 is common to the denominator and the numerator, we're going to have a removable discontinuity, and that's going to create a hole in the graph. This is removable, because if it's common, you can remove common factors. That's a removable discontinuity. But if a 0 is unique to the denominator, that means division by 0, which is going to create a vertical asymptote. And then the last thing you would want to look for is if a 0 is unique to the numerator, then you have an x-intercept, because you're setting the numerator equal to 0. And when you have 0 over some kind of number, that result is 0. But when you have a number on the top and 0 on the bottom, you see how it says NO, no way. You can't do that. That's a vertical asymptote. So this one is okay. Let's say we had a constant on the bottom. This one's okay. You got a 0. So let's give that a try. Find the hole, the vertical asymptote, and the x-intercept of this rational function. So we could do that by factoring an x out of the top, and then the common factors in the bottom would be a 3 and an x. And we want to tear that apart. So watch what's happening here. The first thing, you see the common factor? We just took out that common factor. When x is 0, it was common to the top and the bottom, and that's going to make a hole in the graph. Now, how do you find where the hole is located? Well, you have the simplified form, x minus 3 divided by 3 times x plus 2. So let's just consider, if you put a 0 here, then our numerator is negative 3, and then 0 plus 2, then we have negative 3 over 6 for the y value. This is our y value. See, y equals that, and we factored to get this, and we simplified to get this. So our y value for the whole is negative 1/2. Okay? What's next? Second, in the denominator, x plus 2 can't be 0. So when x is 2, we have a vertical, when x is negative 2, talking and not thinking, we have a vertical asymptote at x is negative 2. And then we have one more thing we want to do. We want to set the numerator equal to 0, x minus 3. And when the numerator is 0, we have found an x-intercept. This is our x-intercept. 3, 0. See, when the numerator is equal to 0, we have 0 over whatever number it would be. If you plug the 0 in here and plug the 0 in here, 0 over 6 is our y value. That's okay. So we found a hole at 0, negative 1/2, a vertical asymptote at x equals negative 2, and an x-intercept at 3, 0. Okay? Next, we're looking at how do you find a horizontal asymptote. So in Algebra 2, you learned there were 3 things you could do. In the first case, when the numerator degree is less than the degree in the denominator, then you have a horizontal asymptote at y equals 0. See, y equals 0 is my horizontal asymptote because the power in the numerator is x to the first, and it's smaller than the power in the denominator. If you think about that for large values of x, you can kind of see where calculus comes into play. You know, we're in pre-calculus. If I had a large number up here and a very large number here, I'm really thinking about 1 over a really, really, really extremely large number. And if that number on the bottom is super, super, super big, then that's roughly going to 0. Okay? So we're looking at the idea or the concept of limiting behavior when we think that way. In Algebra 2, you saw case number 2. That was when the ratio of the leading coefficients were compared. If the numerator degree was the same as the denominator degree, then you just compared the leading coefficients. An example of that would be, let's say, 8x squared minus 1 and 2x squared plus x minus 3. So when we're talking about very large values of x, you see how these are the only things that matter? We saw that in an earlier lesson. And if you had 8 times a huge number times a huge number, and 2 times a huge number times a huge number, that's a form of 1. And we end up with 8 over 2 as our ratio of the leading coefficients. And 8 divided by 2 gives me 4 for the horizontal asymptote. Then case 3 from Algebra 2 was when the numerator was larger than the denominator. In that case, you had no horizontal asymptote, but you could possibly have a slant asymptote, and that's called either a slant or oblique asymptote. And that was in the case when the power was one more in the top than the bottom. Then you could use synthetic division and you could find a slant asymptote. You have no horizontal asymptote. And again, we'll see one of those in our examples here. So here's 3 real quick ones. Can you find the horizontal asymptote for the function and give a reason? In the first one, the bottom power is greater than the top power because the top power is to the 0 power. So that's how we know x to the 0 is smaller than x to the second. So our horizontal asymptote is y equals 0. This one, x to the first on the top is the same as x to the second. So we want to do the ratio, and the ratio is 2 divided by 1. 2 divided by 1. So our horizontal asymptote is 2. And in this bottom one, we have x squared in the top. That's bigger than x to the first in the bottom. So this has no horizontal asymptote. It would have a slant asymptote. In example 4, we're going to practice finding a slant asymptote. And like I said earlier, a slant or oblique asymptote will happen when the numerator is 1 degree higher than the degree in the denominator. And we want to find the quotient using synthetic division or long division. Since we have a linear factor on the bottom, we'll use synthetic division, and the 0 of the denominator would be -5. Then our coefficients in the numerator would be 1, -6, and 7. So the behavior of the slant asymptote is going to act like our quotient. And once we find the quotient, you don't need to consider the remainder at all. That's not important. What is important is that the slant asymptote is the quotient, the depressed polynomial, and our depressed polynomial is y equals 1x minus 11. And this is the part that matters, just the quotient, not the remainder. It's going to be important for most of our course to be able to analyze functions like this without using a calculator. And you can see we're already starting to develop a process for what we need to do. Find the domain, locate asymptotes and holes for removable and non-removable discontinuities, locate any intercepts you have, think about the end behavior, and then find some method to sketch the graph. And we're going to look at that in this lesson and the next lesson. So first of all, we want to find the asymptotes and the intercepts of this one, and then we'll sketch the graph. So my numerator is x minus 3, and I want factors of 6 that add up to be +1, and the factors of 6 have to be -6, so we could use 3 times 2, and we want the sum to be a +1, so if we had a +3 and a -2, that would give us our f of x. This tells me that vertical asymptotes happen when the denominator is 0. So we need a break in the graph at -3, and we need a break in the graph at +2. So we have infinite discontinuities at -3 and +2. Now, here's one thing I like to do. You see that -3 there and that -6 there? If you put a 0 everywhere, then you know when x is 0, the ratio of -3 over -6 is our y-intercept. So we found the y-intercept at 0, 1/2. So it's really, really close here. The next thing you can do is set the numerator equal to 0. So when the numerator is 0, you have your x-intercept at 3, 0. So we can put a dot at 3, 0. Then we can look at the original function and see you have 1x, x to the first, and x to the second. So where is our horizontal asymptote? When the bottom power is bigger, it's at y equals 0. What else do we need to find? Can you think of anything? There's no hole in the graph. Nothing canceled. And here's the first chance. You see how my x-intercept is going to cross over the horizontal asymptote? Now, we don't really know what's happening over here. So you can think if you tested a number, let's say we tested -4. If you think of testing a negative number here, you're going to get -7 in the top. And what's going to happen in the bottom? A -4 add 1 is a -1, and a -4 minus 2 is a -6. So you're going to end up with a negative number over a positive number, which means everything in this section is negative. So I know, without really getting into the weeds here with plotting points, I know that I'm going to hover close to that, and I'm going to have to turn and go down when I get to that infinite discontinuity. So we've kind of figured out that everything in that section of the graph has to be below the x-axis because all the values were negative. And then what happens in here? You see how my y-intercept is right there? Without looking at a calculator, I'm either going to have something like that, or something like that in this section. And again, the way I would find that is I would think about the behavior here. What happens if we put a 1 in here, a 1 and a 1 and a 1? Or what happens if we put a 1 here, a 1 here, and 1 here? You see how it's going to end up being a positive number? And if we had a -1 there and a -1 squared and a -1 there, the same thing's going to happen. On the other side, it's going to be positive. So that tells us the behavior of the graph between the two asymptotes has to look like a little parabola. It's got to go close to the asymptote. It's got to come over here and go through the y-intercept, and then it's got to curve and go up like that. Just based on the behavior of the signs of the y values. And then if we tried 4 here, think about 4 minus 3 is 1, and 4 squared plus 4 minus 6 is, let's see, 14, right? So 1/14 is going to be really, really close to the horizontal asymptote. So it's going to barely be positive, but it's got to cross here, and it can't cross the vertical asymptote, so it has to go down there. This is our first example of crossing the horizontal asymptote near the origin, but the end behaviors, see out here and out here, the end behavior is tending towards 0 because 0 is my horizontal asymptote. It's telling us the end behavior for large values of x, whether they're positive or negative large values. let's look at another interesting case here. So what makes the numerator 0 is our x-intercept. This comes from the numerator. The y-intercept is when we plug 0 into x. What do you get? And then the vertical asymptote, can this ever be 0? No, we can't have a vertical asymptote. Then comparing powers, x to the first and x to the second, our horizontal asymptote is 0. Nothing canceled, so we have no whole, and there's no vertical asymptotes, so domain can be all reals. And we already know what's happening here. As x goes left, y is going to head to 0, and as x goes to the right for large X, y is going to go to 0. And then in this case, because it's not really clear how all of this looks, I probably would make a really quick little table for x and y values. And we know at -3, if you plug a -3 in there, we'll get -1/2. We already know 0, -2. If you plug a 1 into there, you got -1/2 again. So I got -1/2 here, -1/2 here. We already know the x-intercept is 2, 0. And we know that the graph has to hover close to 0 at both ends. So starting over here, I've just got to stay close to 0, come around to here, dip down, go back up, and cross over and stay close to 0. How about that? So that's a strange looking rational graph because we had an addition in the denominator. This one, look at there, slant asymptote. How about that? So x-intercepts, let's see. The numerator doesn't factor, so there's not going to be any x-intercept. And a y-intercept is going to be +5 divided by -2 because we put a 0 for x. -2.5 is the y-intercept. So that's down here. The vertical asymptote will be x minus x equals 2. We can draw that in. Whoop, I want that to be red. Let's do that. Get a red pen. X equals 2. And then we need some synthetic division here. So if we're dividing 2 into the 2 and -3 and 5, remember we just want the quotient, the depressed polynomial. 4 minus 3 is 1, and we don't care about the remainder. So our oblique asymptote is 2x plus 1. So going to our graph here, 2x plus 1 is going to be right there. So we want to go up 2 and right 1, up 2 and right 1, up 2 and right 1, down 2 and right 1, down 2. So we've got a oblique asymptote going across here. And once again, without taking out a calculator, I need to know the behavior of the graph. I don't know if it's over here, over here, over here, over here, but I do see that. And I do know that I've got to stay close to this line. Whoop, not red. Let's do blue. I've got to stay close to the slant asymptote. Have to come up here at 2.5 and then turn and go down. So these are just sketches. I'm not being super accurate by spending time making a table. Then I need to know whether the graph is in this region or up here in this region. So I could go back and think, what would happen if I put a 3 everywhere? And if I put a 3 everywhere, I get some number that's really close to 11. Because we've got 9 times 2, that's 18, minus 9, that's 9, and 5 more. Let me erase this. So we got 14 in the numerator, and we put a 3 here. No, I put a 4 there. Did I put a 3 there? It was a 3. So I got 14. So when we put a 3 there, we're way up here at 14. So we've got to stay like that, and we've got to go off that way. Okay? And again, I'm only making estimates because we're sketching. So we had no hole, nothing canceled. The domain had to skip across 2. 2 was not included in the domain. And then the end behavior, we could say as x went left, so the further the bigger x's go, the y's are going to go to negative infinity. And on the other extreme, as x goes far right, the y values are also increasing, unbounded, to positive infinity. And then we got 2 more to go. Graph the function 2x squared minus 5x minus 3. So first we want to try to factor. Factors of 3 that add up to 5 would have to have a 3 times 2 for 6 there. And if it was negative 6 and positive 1, we could get that negative 5. And then it looks like 4 times 3 would give us 12. And if it was a negative 3, that would give us 1 in the middle. And here's where we're going to have a hole. So plugging 3, because 3 is where the hole is, plugging 3 into the function that's left over, that's 6 plus 1, that's 7. Divided by 7, we have a hole at 3, 1. So I'm going to come over to the graph, and at 3, we're going to have a hole right there at 1. So 3, 1 is the location of a hole. There's a vertical asymptote at negative 4. That's the remaining factor in the denominator. Excuse me a minute. I need a sip of water. Much better. Okay, negative 4. If we compare the powers are the same in the top and the bottom. So y equals 2 over 1 is our horizontal asymptote. You can draw that in. Setting the numerator equal to 0, we would have negative 1/2, 0 for the x-intercept. Plugging 0 into the function, we have 1/4 as our y-intercept. And let's see if we can put those together. So negative 1/2, 0, is an x-intercept. And what was the other point we had? 0, 1/4 was a y-intercept. So we know that the graph hovers toward the horizontal asymptote. It's got to come over here and then go down, heading toward that asymptote. And if we tried -5 here, we're going to have a negative number over a negative number. So our y values are going to have to be positive, and they would be up here somewhere without actually plugging it in. It may be that this branch is lifted up somewhere. I'm not really finding one particular value, but I do know the behavior is up there. And did they want, let's go ahead and write the end behavior. As x goes left and as x goes right, y is going to be approaching 2 in either direction. Okay, we only have one more to go. So analyze and draw. Let's see, can you factor this? 4 times 2 is 8. And we got the difference of 2 squares on the bottom. So a -2 and a +2. And that gives us a hole. So I have a hole in the graph at -2. And if you plug -2 here and -2 here, you get +3/2 or 6/4. We have a horizontal asymptote at 1 because the powers are the same and the ratio is 1 divided by 1. Here we have a vertical asymptote at 2. We have a y-intercept at +2 because 8 divided by 4 is +2. And we have an x-intercept from the numerator at 4, 0. So we have a lot of information, and we can put those pieces together. First, a horizontal asymptote is at 1, and a vertical asymptote is at 2. You have an x-intercept at 4, 0. You have a hole at -2, 1.5. You have a y-intercept at 0, 2, so we're going to hover close here, skip over the hole, go through 0, 2, and turn and go up. And we have to cross here, and we can't go past the y horizontal asymptote, and we can't go past the x vertical asymptote. So we have our graph there. Practice graphing without a calculator. See you next time.